Welcome back to Physics 192. I'm Gerard Blanchard. Last time I introduced the electric field and the equation for the force that the electric field exerts on charged objects, specifically that the vector electric force is equal to the charge of the object feeling the force times the electric field vector, or force is equal to Q times E. F is equal to Q times E. Now, that is a vector equation, so the electric force in the x direction is equal to the object's charge times the electric field in the x direction. The force in the y direction is equal to the object's charge times the electric field in the y direction. And the force on the charge in the z direction is equal to the object's charge times the electric field in the z direction. We worked a couple of exercises applying this equation, and let's do a couple more. Some forms of cancer can be treated using proton therapy, in which proton beams are accelerated to high energies, then directed to collide into a tumor, killing the malignant cells. Suppose a proton accelerator is 4 meters long and must accelerate protons from rest to a speed of 1 times 10 to the 7 meters per second. Determine the magnitude of the electric field that would accelerate these protons. So once again, draw a diagram, list your knowns and unknowns, and go ahead and give it a shot. Okay, let's draw our diagram. I'll draw my x-axis, and we'll have the protons accelerating in the x direction. There's my proton. It accelerates to here. And this is the x-axis, so we'll call this x initial is equal to 0. Vx initial is equal to 0. We're told that the protons accelerate from rest. T initial, we call that 0 as well. They accelerate in the x direction. We don't know what the magnitude of the acceleration is yet. And finally, x final, we're told is 4 meters. Vx final is 1 times 10 to the 7 meters per second, and T final, we don't know. These are protons, so we know that the mass of the proton is 1.67 times 10 to the minus 27 kilograms, and the charge is equal to plus E, which is equal to positive 1.602 times 10 to the minus 19 coulombs. And we are told that the proton is being accelerated by an electric field, so there must be an electric force, Fe, which is equal to Q E, the magnitude, Fe is equal to Q times the magnitude of E. It's in the direction of the positive x direction. And we know that since this is a positive charge, it will feel a force in the same direction as the electric field. So we know that the electric field must be in the positive direction. Sorry, just E. So the electric field is in the positive x direction. Okay, that is everything that we're told. So now we have to bring in our physics concepts, and the two concepts that we're going to bring in are Newton's second law, or non-equilibrium, because the proton is at rest but it doesn't remain at rest, it accelerates, and kinematics, because the particle moves from here to here. So we would have a X non-equilibrium equation, which is AX is equal to the total force in the X direction divided by the mass. And we would also have an X kinematic equation, which is, well, we have to figure out which one, because there are 4 kinematic equations to choose from. We choose the equation that has what we don't need to know in it, and we don't need to know time. So we want our kinematic equation that does not have time in it, and that would be Vx final squared minus Vx initial squared is equal to 2ax times x final minus x initial. Okay. Well, we don't know ax. What is our, so ax is equal to the total force in the x direction. Well, there's only one force in the x direction, and that is the electric force. So the electric force in the x direction would be charge times Ex times the electric field in the x direction divided by mass, or Ax is equal to charge, which is 1.602 times 10 to the minus 19 divided by the mass of 1.67 times 10 to the minus 27 times Ex. Our Ax is equal to 1.602 times 10 to the minus 19 divided by 1.67 times 10 to the minus 27, and that tells us that Ax is 9.59 times 10 to the 1, 2, 3, 4, 5, 6, 7 times Ex, which we can solve for Ex, and so that would be Ax divided by 9.59 times 10 to the 7 is equal to Ex. That's as far as we can go right now, because we don't know Ax. Well, once we figure out Ax, then we can divide by this number, and we'll have the answer to the question that we were asked. How are we going to get Ax? We'll get it from this equation over here, from our kinematic equation. Vx final is 1 times 10 to the 7 squared minus Vx initial, which is 0 squared, and that's equal to 2 times Ax, which we don't know, times x final, which is 4 meters, minus x initial, which is 0. And so we can solve that for Ax. So that would be 1 times 10 to the 7 squared divided by 2 times 4 is equal to Ax. And so we have 1 times 10 to the 7 squared divided by 2, and divided by the quantity of 2 times 4. And that would be 1.25 times 10 to the 13 meters per second squared is equal to ax. So that is the acceleration, 1.25 times 10 to the 13 meters per second squared. And now we can take that acceleration, put it in over here, and we have 1.25 times 10 to the 13, which is ax, divided by 9.59 times 10 to the 7 is equal to the x component of the electric field. And so 1.25 times 10 to the 13 divided by 9.59 times 10 to the 7 gives us 1.30 times 10 to the 1, 2, 3, 4, 5 times 10 to the 5 newtons per coulomb, that's our basic metric units for our electric field, is equal to the x component of the electric field. And so that answers the question we were asked. What the magnitude would be the same as Ex, since that's our only component. So the magnitude of the electric field that would accelerate these protons is 1.3 times 10 to the 5 newtons per coulomb of electric field. Let's do another exercise. A particle with a mass of 2.30 grams and a charge of 10 millicoulombs enters through a small hole in a metal plate with a speed of 8.5 meters per second at an angle of 55 degrees. The uniform field in the region above the plate has magnitude 6.5 times 10 to the 3 newtons per coulomb and is directed downward. And there's a diagram here so that you can see that. The region above the metal plate is essentially a vacuum, so there is no air resistance. There are two questions here. Can you neglect the force of gravity when solving for the horizontal distance traveled by the particle? And secondly, how far will the particle travel in x before it hits the metal plate? So this is another kinematic question for you. And to answer the first question of can you neglect the force of gravity, just calculate the magnitude of the electric force and the magnitude of the gravitational force on the particle. And what you'll see is that the gravitational force on the particle is so small that we really don't need to consider that. So the answer is, can you neglect the force of gravity? Yes, but I would like you to prove that to yourself. So you can see the diagram here. Please reproduce the diagram, drawing your axes, drawing the forces on the particle, and then use your kinematic equations and Newton's second law to answer the question that's asked, the second question. Go ahead and give it a try. Okay, let's reproduce the diagram that we were given. Here's the particle. I'll label it with a plus since it's a positive charge. And here's the plate, which will also make the x-axis. We'll make y perpendicular to that. The particle enters with V initial equal to 8.5 meters per second, which means that it's moving in both the x direction and the y direction. So we would have Vx initial and Vy initial. We're told that there is an electric field which is directed downwards, or in the negative y direction, and it has a magnitude of 6.5 times 10 to the 3 newtons per coulomb. And we're told that the mass of the particle is 2.30 grams, which we'll have to convert. 1 kilogram is the same as 1,000 grams. So the mass is equal to 0.0023 kilograms. And the charge is equal to 10 millicoulombs, and there are, well, one millicoulomb is equal to 0.001 coulombs, or 1,000th of a coulomb. So that gives us canceling out our millicoulombs, that gives us a charge of 0.01 coulombs. Okay, let's see what else do we have here. Okay, well, we have a right triangle right here with our initial velocity going up at an angle of 55 degrees. So we can calculate both our Vx initial and our Vy initial. And Vx initial is going to be 8.5 meters per second. And actually, I'm going to leave out the meters per second, times the cosine, so 8.5 cosine of 55 degrees. And Vy initial is going to be the hypotenuse of 8.5 meters per second times the sine of 55 degrees. So 8.5 sine of 55 degrees. And let's calculate what those two are. 8.5 times the cosine of 55 degrees is we'll call it 4.88 meters per second, and 8.5 times the sine of 55 degrees is 6.96 meters per second. Okay. And the particle will feel a downward force due to this electric field. So even though it's initially moving up, that downward force will cause it to curve down just like a projectile. So in a parabola, just like a projectile. So I'll go ahead and draw a parabola here, showing the particle initially moving up and then curving over and coming down to x final and y final. Well, x final and y final depend on what x initial and y initial are. So we'll call x initial equal to 0 and y initial equal to 0. We'll make this starting point the origin. So x final, we don't know. That's what we're looking for. Y final, well, if the plate is y is equal to 0 and the particle comes back to the plate, then we know that y final is equal to 0. And this x final is what we're looking for. Okay. We also are going to need, eventually, the acceleration, ax and ay. So I will write here that ax is unknown and ay is unknown. And we can finally say that T initial is equal to 0 and T final, we don't know. And with all of that, we have reproduced all of the information that is in the question statement. All of the information that was in the question statement, either explicitly or what we could infer from the question statement. So we haven't applied any physics to this yet. We've just taken what was given in the question statement and what we could imply from the question statement. So let's see. Let's look at the forces. Well, as we said, since there is an electric field here, the particle is going to feel a downward electric force. It's also going to feel a downward gravitational force. Let's calculate the magnitude of those two forces. Okay, the magnitude of the gravitational force is equal to the particle's mass times g, and the magnitude of the electric force is equal to the particle's charge times the magnitude of the electric field. So Fg is 0.0023 kilograms times 9.8 newtons per kilogram, and Fe is equal to 0.01 coulombs times 6.5 times 10 to the 3 newtons per coulomb. And actually, I don't normally write out the units there, but since I did, I'll write out newtons per coulomb. Okay. So Fg is 0.0023 times 9.8, and that is 0.0225 newtons, and Fe is equal to 0.01 times 6.5 times 10 to the 3, or 65.0 newtons. So you can see that the electric force is much greater than the gravitational force, and in fact, the gravitational force is in what would be the fourth significant figure of the electric force, which we've rounded off anyway. So we're not worried about a contribution as small as a gravitational force. So the gravitational force, we would say, is negligible in this case. So we would say that Fg is negligible. We don't need to worry about it. So we will go with the only force on the particle being the electric force. Fg is just too small for us to worry about. It's within the round-off error of Fe. Okay, so now we know that Fe is 65 newtons. Now we have to bring in, well, we brought in our physics here, but now we need to bring in the physics to answer the question of at what distance does the particle hit the metal plate? Well, we will need an acceleration equation in the y direction, an acceleration equation in the x direction. We will need two kinematic equations for x and y. So first off, we'll use Ax is equal to force total x over mass, or Ax. The total force in the x direction is 0. The electric force is completely in the y direction. So the total force in the x direction is 0. Dividing by the mass, we still get that the acceleration in the x direction is 0. So the particle will not accelerate in the x direction. How about the y direction? AY is equal to force total y over mass, or AY is equal to QEY divided by mass, or AY is equal to 0.01 coulombs. Actually, I'm going to write over the coulombs there. 0.01 times EY, which is in the negative y direction, so negative 6.5 times 10 to the 3 newtons per coulomb, divided by the mass of the particle of 0.0023 kilograms. And that gives us that AY is equal to 0.01 times negative 6.5 times 10 to the 3 divided by 0.0023, and that gives us negative 2.83 times 10 to the 4 times 10 to the 4 meters per second squared. So the here we go. AY is 0.01 times negative 6.5 times 10 to the 3. That's the charge and the electric field, the y component of the electric field, and it's negative because it's directed downwards, divided by the mass of 0.023, and all of that gives us an acceleration in the negative y direction of 2.83 times 10 to the 4 meters per second. So the acceleration of the particle is in the negative y direction. The acceleration of the particle in the x direction is 0. So this is actually familiar. This is exactly what our projectile situations were like before. Okay, so we figured out the acceleration in the y direction, the acceleration in the x direction. Now, knowing that, we want to figure out at what x does the particle come back to the plate. We're not interested in the speed of the particle or the x or y components of the velocity of the particle when it comes back to the plate. So that would be Vx final, which we don't know, Vy final, which we don't know, and we don't need to know. We're not being asked for these x and y components of the velocity. So the kinematic equation that we're going to choose in both cases is going to be our kinematic equation that doesn't have Vx final and Vy final in it. And those are going to be x final minus x initial is equal to Vx initial times t final minus t initial plus 1/2 ax times t final minus t initial squared, and the same for y. Y final minus y initial is equal to Vy initial times t final minus t initial plus 1/2 ay times t final minus t initial squared. Okay, x final is what we're looking for. minus x initial, which is 0, is equal to Vx initial, which is 4.88 meters per second, times T final, which we don't know, minus 0, plus 1/2 AX times T final minus T initial squared, but AX is 0. So all of this term is 0, so I'm just going to write 0. Okay, and that gives us X final is equal to 4.88 T final. We don't know T final. If we can get it from this equation, however, then we'll be able to answer the question of what is X final. Okay, well, let's substitute in for Y final. Y final is 0 minus Y initial, which is 0, is equal to Vy initial, which is 6.96 times T final minus T initial, which is 0, plus 1/2 AX, which is negative 2.83 times 10 to the 4 times T final minus T initial, which is 0, squared. Okay, and that gives us 0 is equal to 6.96 T final minus 1/2 of 2.83 times 10 to the 4 T final squared, or I'll add this term to both sides, and I'll get 1/2 of 2.83 times 10 to the 4 T final squared is equal to 6.96 T final. And you can see that on this side I have T final squared, and on this side I have T final, so I can divide both sides by T final, which T final divided by T final would just give me a 1 right here, and T final squared over T final just leaves me with T final. So that says, I'm running out of room here, but we'll get to it, T final is equal to 6.96 divided by 1/2 of 2.83 times 10 to the 4, which is equal to, and when you do your division, be sure to put this parentheses around the 1/2 times 2.83 times 10 to the 4. Otherwise, your answer won't come out right. Okay, so 6.96 divided by parentheses 1/2 times 2.83 times 10 to the 4, close parentheses, and that gives us a T final of 4.92 times 10 to the minus 4 seconds. 4.92 times 10 to the minus 4 seconds. So the time that it takes the particle to go from here to here is just 4.92 times 10 to the minus 4 seconds. And now that we have that, we can substitute that in for here, and we get X final is equal to 4.88 times 4.92 times 10 to the minus 4, our x final is equal to 4.88 times 4.92 times 10 to the minus 4. And we get that x final is 2.4 times 10 to the minus 3 meters. 2.40 times 10 to the minus 3 meters, or 2.4 millimeters. And that is the question we were asked. Where does this particle hit the plate again? It hits the plate at 2.4 times 10 to the minus 3 meters. So those are some examples of using the electric force in kinematic and non-equilibrium, or Newton's second law, situations. Now we'll go on to the concept of electric potential energy. So we'll be able to use electric field concepts in potential energy or energy situations. Let's go back to gravitational potential energy. If you recall, the gravitational potential energy of an object in a constant gravitational field, so meaning close to the surface of the Earth, where the gravitational field was constant, we were able to use the equation UG, our gravitational potential energy, is equal to m times g times h. So the gravitational potential energy is equal to the mass of the object that we're moving times g, the gravitational field strength, times h, the height, which is the distance that you move opposite the direction of the gravitational field. Remember that everywhere near the surface of the Earth, the gravitational field is downward, whereas height increases upwards. So you increase in gravitational potential energy when you move opposite the field. Well, the expression for electric potential energy in a constant electric field is very similar. Let's take a look at that. UE, or the electric potential energy, is equal to minus Q times EX times X, which would be minus the charge of the object that's moving, times the amount of the electric field in the X direction, times X, the distance that you move in the X direction, minus the same thing for Y and Z, minus QEY times Y, and minus QEZ times Z. So why do we have three terms here? Why do we have both X, Y, and Z? Well, for gravitational potential energy, we generally set one of our coordinate axes, the y-axis, to be in the upward direction, so that height was always increasing in the y direction. When we're dealing with electric fields, we don't know ahead of time whether the electric field is going to be in the x direction, the y direction, or the z direction, so we have to consider each one of those components separately. Now, why is it minus q? Why do all of those terms have a negative sign? Well, the reason for that is that EX is the amount of the electric field in the positive x direction. So if EX were positive, meaning the electric field was pointing in the positive x direction, and we increased x, we would be moving in the direction of the field, which for a positive charge should actually give us a decrease in potential energy. Just like for a gravitational field, when you moved in the direction of the field, which is downward, you would decrease your potential energy. Same thing with the electric field. Whenever you have a positive charge, moving in the direction of the electric field decreases your potential energy. So if we have an electric field in the positive x direction, and we want the potential energy to decrease in the positive x direction for a positive charge, then we would have to write UE is equal to minus Q times EX times X. And the same thing goes for Y and Z. So just remember that that's one difference between the expression for the gravitational potential energy and the expression for the electric potential energy. What are the differences? Once again, instead of mass, we have charge. Instead of gravitational field, G, we have electric field, E. And instead of height, we have X, Y, and Z. And also we have a negative sign. So the expression, once again, for the electric potential energy in a constant electric field is UE is equal to minus Q times EX times X minus Q times EY times Y minus Q times EZ times Z. Just remember that for a positive particle, you decrease in potential energy. For a positive charge, you decrease in potential energy when you move in the direction of the electric field. And we'll do some examples of this, and it should become clear as we do some examples. But first, I'm going to introduce another concept. I'm going to introduce the concept of electric potential. So let's take our equation UE is equal to minus QEX times X minus QEY times Y minus QEZ times Z. What we can do here is we can factor out the charge and simplify this equation to U sub E, or the electric potential energy, is equal to Q, the charge, times V, where V is everything else in that equation, or specifically V is equal to minus EX times X minus EY times Y minus EZ times Z. So our new expression for the electric potential energy, UE, is equal to charge times V. V is called the electric potential. That is the name of that new quantity that we defined, V. The units of electric potential must be joules of potential energy per coulomb of charge, because we could solve that equation for V is equal to U over Q. So the units of electric potential are joules of potential energy per coulomb of charge, and we're going to give that unit a new name. We're going to call that the volt, and we're going to write it with a capital V. But be careful. The symbol for the quantity electric potential is going to be an italic V, and the symbol for the unit is also going to be a capital V, but it's not going to be italicized. And when I write it, I'm going to write it with little serifs so that you can distinguish it. You can distinguish the quantity from the unit. So we've rewritten the electric potential energy to be equal to charge times electric potential, V, where the electric potential is minus EX times X minus EY times Y and minus EZ times Z. So you can see that the units of the electric field, newtons per coulomb, could also be written as volts per meter, because in the equation for potential, the electric field in volts per meter times X in meters would give us units of volts. So sometimes you will see the electric field written in newtons per coulomb, and sometimes you'll see it written in units of volts per meter, but those are equivalent units. Newtons per coulomb and volts per meter are equivalent units. So, to summarize, we have defined a new quantity, the electric potential, and the electric potential energy is equal to the charge times the electric potential. Next time, we'll come back to that, and I will give you some exercises to work applying electric potential energy. Until then, think physics.